Hello, this video is about photon inhibition for single photon sensors. Single photon avalanche diode sensors or SPADs are based on avalanche multiplication. A single photoelectron causes a chain of impact ionizations which results in a strong photocurrent at the end. This allows photons to be individually counted or timed. Precise timing information is utilized in LiDAR, but passively measured photon counts also have many applications like HDR or low light imaging under motion. Recent works have improved on practicality, and some commercial SPAD sensors have also been made, so SPAD imagers may become even a general purpose vision tool going forward. However, there is a practical challenge that is unique to SPAD image sensing. For a conventional large format CMOS sensor, its power consumption does not depend on the amount of light coming in from the scene. But in a SPAD, on the other hand, each photon detection comes with a significant energy cost. And so the power consumption increases with scene brightness and sensor resolution. This makes it challenging to realize high-resolution SPAD sensors in form factors like cell phones or mobile robots. Now, if each photon detection costs energy, we can ask what photons should we even spend this energy on? So here on the left is an example image we may want to capture with a SPAD image sensor. Now, if we were to capture it directly, most of the detections are dominated by the very bright pixels in the background, which are almost saturated. So they don't give us good reconstruction quality either. So what we want to do is to balance result quality against the energy cost, for which we propose the metric of detection efficiency, which is the ratio of signal to noise ratio and the number of photon detections at a pixel. It captures this sense of diminishing returns on signal quality as pixels start to saturate. Metrics like this could be used to guide capture policies for SPAD sensors. We explore computational approaches to control individual SPAD pixels electronically. This is done by setting the SPAD's bias voltage. When a pixel is disabled, photon avalanches are not triggered, and so their energy cost is eliminated. Inspired by similar mechanisms in the human visual system, we call this photon inhibition. We design lightweight operations called inhibition policies that update the pixel state on the fly, based on a local and short history of previous frames. We extend a baseline clock recharge system where the SPAD is reset only at a fixed interval. Within one clock period, only one photon can be detected. On top of clocked recharge measurement streaming in, we apply a spatiotemporal linear filter, and if the result S crosses a threshold eta, we disable the pixel for a fixed number of recharge periods tau h. No photons are detected in this period. Tau h denotes a hold-off period and can be considered a computationally imposed dead time. In this simulation of a single static image, we fix the total avalanche energy consumption on both sides. The text is clearly readable under inhibition, but the conventional capture is too noisy. On the right, we see inhibition patterns for each of the exposure times, where more inhibition means fewer measurements are made at that pixel. The shortest exposure only inhibits modestly, and even that is only at the brightest pixels, so the measurements are uniformly spread. But the longest exposure allocates most of its measurements to the darkest areas of the scene. More broadly, inhibition policies can be designed for other vision tasks like optical flow or object detection and tracking, or as shown here, edge detection. As data from the SPAD streams in, the inhibition policy adapts to favor informative pixels that contribute more strongly to the edge map. For equal edge detector performance, inhibition reduces photon detections up to 30%. And now we look at a different inhibition policy, which builds upon clocked recharge implemented with a varying interval. This results in a form of exposure bracketing. The long exposures heavily reduce the total number of photon detections. The idea in look-ahead inhibition is to disable a long exposure if it is expected to become saturated anyway. We can see this through an example. In the shortest exposure, 2 photons are detected out of 3 measurements, and the capture keeps going. In the medium exposure, it is 3 out of 3. This crosses the second threshold, so we disable the longest exposure because it is also predicted to saturate. This prevents all photon detections in that exposure. These computations target simplicity and maintaining a high frame rate. This binary image sequence is captured by a SPAD sensor array. Compared to standard exposure bracketing, look-ahead inhibition disables a large fraction of the pixels in the longer exposures because they cross the saturation threshold. In our experiments, it prevents over 90% of photon detections in bright scenes. Image quality is improved with multiple captures and burst reconstruction techniques. This longer sequence has large variation in lighting. The inhibition policy adapts to let in more photons when lighting is weak, but is more aggressive in strong light. Still, over 90% of photon detections are prevented in total over the whole sequence. Here is one of the lower light frames. Other vision tasks and performance metrics can also be targeted, similar to the first policy. Here we see object detection with only around 5% of the original photons. So SPAD sensors are exciting, but also present this challenge that every photon comes at a cost, which motivates this question of what photons should be detected. Photon inhibition is a computational imaging approach to this problem and can be tuned to the specific vision task at hand. Since there is this new step in the image capture pipeline, there is scope to optimize both on the algorithms and on the hardware design side, perhaps even jointly. For more information, please visit our webpage. Thank you.